Alright, so today is the last lecture of this whole series, and this will end with a description of some waves. We talked about waves in context of light when we were talking of diffraction, interference and refraction, other things. We talked about wavelength of light or frequency of light. The wavelength, we say that it is from 400 nanometer to 700 nanometer for visible light. Frequency is some 10 to the power 15 oscillations per second and all that. In the previous lecture I showed you some waves. For example, I showed you a wave going on a long spring. We deflected one part of the spring and that hump propagated down the line, and we said that this is a wave. Similarly, we had those sticks in the sellotapes, and then I gave some angular displacement at one end, and you saw that some kind of disturbance was traveling down the line, and we said that it is a wave. I will show one more wave today that will be on water. The question that you should ask is, what is the wavelength and what is the frequency in all these waves that I am demonstrating, for which I had written equations like some function of x minus vt and all those things. So, where is that wavelength and where is the frequency? Enjoy this experiment and also think on this question. So, I have this thali here, steel thali, and in the steel thali I have put some water. Now, I will make some disturbance in the water, just touch near the center, and you see if something is traveling on the surface of this water. So, what do you see? From the center, something goes towards the rim of this thali, reflects from all sides, collapses at the center, and again spreads with reduced amplitude, of course, towards the rim, and so on. So, what is the wavelength and what is the frequency in this water wave? When I talk of frequency, I do have some kind of oscillations in mind. Frequency is per unit time. How many times did that motion repeat? So, something should keep oscillating, then only you can count how many times the motion is repeating. But in the waves that I have shown, the things just gets displaced and comes back. It is not oscillating continuously. In the water wave, think of some water mass, the wave comes, passes through that point, and that water mass is lifted, goes down and stays there. In that spring wave, we gave some disturbance, that hump reaches somewhere and the turns there, they get displaced and come back and stay there. It is not oscillating. So, I cannot talk of frequency here. I cannot talk of wavelength here. At a given instant of time, I do not have repetition of the pattern. So, I cannot talk of wavelength. For that, you must have a continuously oscillating things, a continuously oscillating waves, a wave which is continuously being created at some point and from where it travels. What will be the equation of such a wave? For oscillations, you know, for a particular frequency, the oscillation, simplest oscillation is your simple harmonic motion. So, I said that if the wave is going in x direction, its equation should be of this type, whatever quantity which is changing in space and time should be some function of x minus vt. And all the experiments that I had shown will confirm to this if you take proper x axis and all that and make some approximations, of course. Now, if you want oscillations at a particular frequency, then the functional form of this gets narrowed. One very common simple easy to deal in mathematics and very, very important. Function will be when you have oscillations which are sinusoidal, sine function or cos function. So it's, let's say, cos of x minus vt should be there, and dimensionally the argument of cos should be dimensionless. So you should have some multiplying factor here. It's like this, which you can also write a cos kx minus omega t, where k into v is omega. Now this is, you are familiar with this. There is a kind of a simple harmonic oscillations. If you fix some x in your medium, some portion, some small portion, so fix that x, it varies with time, and that oscillations is simple harmonic oscillations. And if this is the kind of wave, then it will have a periodicity in space and a periodicity in time. At a particular instant, if you see, it changes with x, and that also is this cosine function. So you will have periodicity in the space, and therefore this cos function, because of this cos function, if you plot, it will be like this. If you plot cos kx minus omega t for a given t, and this side is now x, and this is wavelength, this is wavelength, and you fix x and c as a function of time, then also it oscillates, and that will be again similar looking function cos kx minus omega t, and this time for a given x. So this will also be of that same time, but this time it is time here, and then this is the time period, capital T. This is the time period. So x is fixed, a particular portion, it oscillates, and how much time does it take in one oscillation? That is t, and this t and this omega are related. This t is 2 pi over omega, and your frequency, which is 1 by time period, is omega by 2 pi. Okay. So now I will demonstrate a kind of wave which will roughly follow this pattern, where you will be able to see what is the wavelength, and perhaps also get a feel of frequency. So here is the apparatus. You have this vessel made of transparent acrylic, and in this vessel we have put some water, and then you have this bulb. So the light from the bulb falls on water, then it goes through the water and the bottom of this vessel, which is transparent, and falls on this white sheet. These are all frames, iron frames. So you concentrate on this area. This is a plain paper, white paper, so you concentrate on this area. Here you have a coin. Here you have a coin which we have placed here, and you can see the shadow of this coin here on this paper. This is placed to give you a size scale here. You can measure the diameter of this coin, and here the diameter of this shadow will tell you how much is 1 centimeter and all that. Okay. Now if I disturb this water surface, what happens on this plain paper? See, right? We disturb the surface of the water, and because of that you have different curvatures at different points, and then the light which is falling on that surface which is now curved. So things will be transmitted according to the laws of refraction, and the intensity of refracted light will be different at different points. So that way whatever is there on the surface, the structure on the surface, somehow it will be imaged on this paper. Of course, it will have its own modification, light will do some modification, you will not exactly get what is happening here, but most of it you can get what kind of disturbance is here, that you can see on this paper. Just see this. So, the wave is generated from the point where I touch the surface, and then it spreads as a circular wave, it goes radially outward on the surface, and then of course, it meets this walls and it reflects from there. There is a damping, so reflected intensities are much smaller, reflection are from all four surfaces. So, you have varieties of beautiful patterns which are made. I have a bead here, connected to a speaker, and that can be oscillated. This bead can be oscillated. And when it touches or it disturbs the water surface, then waves are generated. There is some electronics behind. So, using that electronics, I can give it controlled oscillations of desired frequency. So, I can oscillate it at low frequency or high frequency, and that can be adjusted through that electronics. All right. So, now I am starting the experiment, and I switch this power on, so that some oscillation has started. Now, if you look at the pattern on this plane sheet, you can see some whitish line and some grayish blackish lines, and they seem to travel outward from some center, and there is a periodicity in space. If you think of some instant, you have a white line, curved line, then you have another white line, then you have another white line, then you have another white line. So, there is a periodicity in space, and the separation between consecutive white lines or consecutive grayish lines, that is the wavelength. So, when the source oscillates in simple harmonic motion or periodic motion, it creates waves with wavelengths. You can now talk of wavelengths, and frequency, of course, you can talk of frequency. Your bead is oscillating, so all particles are oscillating with that same frequency. So, that is the frequency of the wave. Now, I will increase the frequency, and you look at the wavelength, whether it increases, decreases, or remains the same. So, I am increasing the frequency. See what happened to the wavelength. The separation between the consecutive whitish line and consecutive blackish line, what happens to that separation as the frequency is increasing, and see that as I increase the frequency, the wavelength is decreasing. Here is a question for you. We are showing the pattern on this white paper at a particular instant. The shadow of the coin is also there. The diameter of this coin is 2.5 centimeters. From this you measure the wavelength in this pattern. So, in all the experiments that I had shown, you saw that when waves meet the boundary, they reflect from there. And if you have this continuous wave formation like this oscillating bead, you are sending the waves, and waves are also reflecting, and both meet at the same place at the same time. Then you have another phenomena which we call standing wave formation, in which at certain points there are very small amplitudes of oscillations, at certain other points there are large amplitudes of oscillation, but as a function of time everything looks stationary. So, let me do some mathematics, and then we will do experiments on that also. So, suppose you have two sine waves, one going in plus x direction, other in minus x direction, one ongoing, another reflected. So, the equations, you can write it as some disturbance, some displacement. This is the ongoing wave. So, A sine kx minus omega t. And the reflected wave which comes in the negative x direction, for that the equation will be A sine kx plus omega t, x minus vt, x plus vt. So, the net is sum of these two, and that will be, add these two, 2a sine kx and cos omega t. Now, there is very special thing about this. It contains two waves, one going in positive x direction, another going in negative x direction. But then at places where this kx is 0 or integral multiple of pi, so at places where this kx is equal to 0, pi, 2 pi, at these places this is always 0. This net displacement, net disturbance is always 0 for all time, any t, if this kx is an integral multiple of pi, this is 0. So, at these positions your displacement is 0 always. These positions are known as nodes. And then you have another positions midway between these, where kx is pi by 2, 3 pi by 2, 5 pi by 2, or the integral multiple of pi by 2. In that case, this is always 1 or minus 1, does not matter, because this is anyway going from plus 1 to minus 1, minus 1 to plus 1. So, here the amplitude of oscillation, this is the amplitude, this cos omega t is the time variation and this is the amplitude. So, this amplitude will be 2a maximum. So, at certain positions particles are vibrating with large amplitudes, at certain other positions they are not vibrating at all, in between they have smaller amplitudes and so on. So, these maximum amplitude positions, they are known as antinodes. So, that would mean in a medium, if I send a wave and if there are boundaries and it reflects, maybe in that space, in that medium, somewhere you do not have any disturbance, somewhere you have large displacement and all that. So, let us see an experiment on a string where this kind of thing does happen. So, here is the apparatus. We have a string here. One end of this string is tied to a rod. This rod goes into some coil and so on, and this electronics is all to vibrate this rod. And when this rod vibrates in a very small amplitude, in fact, you will not be able to see, that sends waves on this string, and on the other side this string goes over this pulley, and then some weights are there on the other side, and this is in some tension. So, that wave goes here, reflects from the pulleys, and then the two interfere to give you standing waves. So, if the tension, the frequency, all those things are nicely matched, you may expect some nodes and some antinodes on this. So, let us see. So, now you can see in the middle the string is vibrating with somewhat large amplitude, whereas if you go towards the end, that amplitude of oscillation decreases, and here at the end here this is almost 0. So, this is node Here in the middle you have antinode, and then if you go on this side, again the amplitudes decrease, and finally here it is again a node. So, this is the fundamental mode of vibration for this string. So, here is a question for you. We are showing you the shape of this string as seen by the camera at a particular instant, and you see the edge portion is much sharper than the middle portion near that antinode region, in the middle region. So, the question is the same string which is going up and down, why at the edges this seems to be much brighter than in the middle. Okay, so here you see another set of parameters. We have changed the tension by changing the weights on the pan hanging from the pulley. We have also changed little bit this length also, and you can see that now this point is not vibrating at all. This is a node here, no one is holding this point, no one has clamped this point. This is free to vibrate, but even then it does not vibrate. So, this is a node, this is a node where it is tied, this is a node where it is meeting the pulley, and in between two nodes here you can see the amplitudes are large. This is an antinode, this is another antinode. So, in this configuration, when the string is vibrating in two loops, you have 3 nodes and 2 antinodes, because the frequencies, the tension and other things are matched accordingly.